Okay, our last example in this section is something called escape velocity. And I'm going to start by defining escape velocity. And so here's that definition here. Escape velocity, this is a very sort of simplified definition. Escape velocity is the minimum velocity with which an object must be launched so that it is able to overpower the gravitational pull of the Earth. In other words, it's the smallest velocity number so that when we launch an object from the surface of the Earth, that velocity, this minimum velocity, this velocity that we find here, the answer to the question, what is escape velocity for this object, is the number uh, that takes this thing far enough out into space so that it won't return, right? So there's at the point at which it reaches whatever the distance it needs to go is, it's no longer in the clutches of the gravity of the Earth, the gravitational pull of the Earth, right? Once it gets to that point, it can either keep going or it can float there forever. But the point is that this thing we call escape velocity is a velocity that will do this job. Get an object far enough away so that it won't ever come back, right? It's outside the gravitational pull of the Earth. It's the minimum velocity for which this is true for a given object, right? If this is a p, then that number is going to be small because the amount of velocity required to shoot a pea into space far enough it won't come back is a lot less than, say, for example, a bowling ball or a boulder. But whatever the minimum velocity is for that object, it's going to be a fixed number, right? Once we figure out what the minimum velocity is for a particular object, it will be a constant. Now, there's an assumption being made here that's actually explicitly stated in your book, but is not in the definition that I've written here. And that's partially intentional. I wanted to make sure we actually addressed it. Let's take an object. I'm going to say a bowling ball, just because I guess I'm kind of in that mood today. Let's call it a blue bowling ball. And let's say that thing weighs 10 pounds. If I choose to launch this thing, I can launch it in any angle that I want, right? I can launch it off this way, or I can launch it almost parallel to the tangent of the Earth's surface at that point. Just shoot it along the ground. But escape velocity is defined as being the minimum velocity required to do this when the object is shot straight up into the air. In other words, so that this is a perpendicular. Now, we may not choose to shoot it straight up in the air. We may choose to shoot it off in this direction, but the escape velocity required, or the velocity required to send it off in this direction until it escapes the Earth, may be a different number. Escape velocity specifically is defined as being the number required when it's shot straight up into the air. So that's an important distinction to make. That's an important piece of this definition. And although it's not written here, it is written in the description of this description of the problem in the example 4 in your textbook. Now, I said I wasn't going to do the exact examples in the textbook, but in this case, I think I will, because what we're doing in this example is simply deriving the formula for escape velocity, among other things. So let's take a look at how your textbook sort of walks through this problem. I'll start by rewriting the problem, but I think I'm either going to need to erase my definition or go to a second screen at some point, because I feel like this is going to take a lot of space. So I'll rewrite the problem and we'll go from there. I'm going to take it a step at a time, and I'm going to write the problem out in a slightly different order than is actually written in your textbook. I'll get all the information in there eventually, but I have a reason for going a little out of order. So let's read through this first sentence. A body of constant mass m, so we don't know what m is, but we know it's a constant value, is projected in a direction perpendicular to the Earth's surface with an initial velocity of v sub 0. Now, one could argue that a direction perpendicular to the Earth's surface is down into the Earth, and that's why your textbook makes the point of saying it's projected away from the Earth, but I'm trying to save space, so I've written it that way. The sentence containing the instructions for this particular part of the problem reads, find an expression for the velocity during the ensuing motion. That just means during the motion that the projectile undertakes after it's launched. So our job is to find an expression of velocity for a projectile leaving the surface of the Earth. We're given the mass of the object is m, and we're given a variable to use for its initial velocity, which is v sub 0. We are also told to assume that there is no air resistance. Well, there is air resistance. There's always air resistance. But in this case, we don't quite have the tools we need to be able to take that into account. So we will be ignoring air resistance. It also tells us, though, to take into account the variation of the Earth's gravitational field with distance. In other words, as an object goes out into space, the amount of effect that the Earth's gravitational field has on it varies according to how far away it is at any given time. The farther away an object is from the Earth, the less pull the Earth has on that object, until eventually it has no pull at all. We are supposed to take the variation of this pull on the object. We are supposed to take that into account. Unless you've had some physics, you may not know what that is, which would be fair. In fact, if you have had some physics, I don't know where this is taught in physics. The good news is that the gravitational force, gravitational pull on a mass is just inversely proportional to the square of the distance from its launch point. Well, actually, it's proportional to the square of the distance from the center of the Earth. And that's given by, and I'll use the same formula as given in the book, and that is W of x equals negative k over the quantity x plus capital R all squared. Now R is just the radius of the Earth, and that is a known constant. But we'll be using R throughout this problem because that allows us to apply the same formula, for example, once we've figured out what it is, to launching a projectile off the surface of Jupiter or the moon, right? So if we have a different radius there, we need a different value. So we'll stick with R, but we know it's a constant. Now, we said that what we were trying to establish with this formula here, and we're just giving it to you, right, is that the gravitational force acting on a mass is inversely proportional to the square of its distance from the center of the Earth. This x stands for how far away the thing is from the surface of the Earth. So r plus x is this entire length here. And the value of k is what we call a proportional constant. It's just some constant value. It happens what we know that what that force is at the surface of the Earth, right? When x is 0, we happen to know that that force can be given by negative mg, where m is the mass in question here. So it's the same mass as we're talking about here. That's our m. And g is gravity, essentially. G stands for gravity. But what it really stands for is acceleration due to gravity, and that's at sea level. And that's what this is here, is at sea level. No, not on top of a mountain somewhere, but right at sea level. So what that means is that k is equal to mg r squared, because our formula is telling us that the force of gravity is inversely proportional to the square of the distance from the center of the Earth, and the inversely proportional to part is represented by this this constant. So that constant is at sea level, the force is negative m times g, but the constant has to take into account the radius of the Earth. So our constant is just mgr squared. K is equal to mgr squared. And that means I can write this formula this way. We don't need this down here anymore, so I'm going to erase this. I just used that to set up the formula. And now that we have our formula, we can take a look at it from a slightly different perspective. What does it mean? Well, one thing to consider is that while we're shooting this thing off into space, we are applying some means of projecting it. We are giving it an acceleration. We have considered the force of gravity as it changes according to the projectile's distance from the center of the Earth, and that we've been told not to worry about air resistance. So we've pretty much considered everything, and there's nothing else acting on this projectile except for those things we've already talked about. And I've been describing this formula for a kind of force, is the force of gravity, right? And one way to think about force, again, you might not have seen this if you haven't had some physics or remember it from previous calculus classes, force can be described as mass times acceleration. Well, if I write mass times acceleration here for my W of x, which is representative of a particular force, that due to gravity, then my formula looks like this. But now, because of the context that I'm in, and because I know something about acceleration, I can change the way I write acceleration. I'm going to write that as the derivative of velocity with respect to time. And now I have a differential equation. One of the problems I see here is that my differential equation appears to be in terms of x, but my derivative appears to be in terms of time. Well, is in terms of time. This is a function of x, but this is a derivative of a function with respect to t. So we need to fix this so that it is in terms of x, since that appears to be my independent variable here. So let's use the chain rule to rewrite this problem as dv dt like this, dv dx times dv dt. Just rewriting the rest of the problem. And let's take a look at what each of these pieces is now, what it represents. Mass is mass, as above here. The right-hand side is the same, and it's in terms of x. So we want the derivative of velocity, an acceleration expression, but we want it in terms of x. So we now have that here. But what is dx dt? Well, that's the derivative of x, which we defined here as being the distance from the surface of the Earth with respect to time. The distance, the derivative of distance, the derivative of position is just velocity. So I can rewrite this one more time as mv dv dx equals. And then your textbook does this a couple of steps before, and I just forgot. I wasn't quite paying attention. I can cancel the m's from both sides. So let's actually erase those because now we don't really need them. And so this is a differential equation, which once we solve it, will give us what we were asked for here, an expression for the velocity. But we need to solve it first. So let me make a little bit more space over on the right-hand side. I'm going to erase the right-hand side. So if you need to make notes of that, pause the video now and take that down. And then once I've erased it, I will carry on by taking the next step to solve this differential equation. Okay, so I've erased the right-hand side. I've drawn a little dividing line just to help me keep my work straight. And I'm going to make the observation here, once again, that this is a separable differential equation. If I multiply both sides by dx, I'll have all my x's on this side, and I don't need to do anything with my v's because I'll just have a v dv left when I do that. So let's do that first. We'll multiply both sides by dx, and then I'll rewrite the problem. V dv equals negative gr squared over the quantity x plus r all squared dx. Sometimes this process is called separation of variables. You'll see in some textbooks, like ours, calls the section separable equations, and other textbooks call the section by the technique, which is separation of variables. Well, I have separated the variables, so now I'm ready to solve this differential equation. It's not a linear differential equation, because if I were to expand this, my independent variable would have a term that that variable would be squared. I'd have an x squared here. So it's not a linear differential equation, but because it's separable, we are still in a position to be able to integrate both sides, and I'm putting my integral symbol there just because I know I can pull that negative out front. In fact, I can pull the gr squared out front, right, because it's a constant. Let's integrate the left-hand side. It's the integral of v with respect to v. That's pretty straightforward. It's just v squared over 2, or 1/2 v squared, if you prefer, equals negative. Let's rewrite this as, I'll pull the constant out front, and then I'm going to rewrite it as the integral of the quantity x plus r to the power of -2. And I think that will make it easier to see what the integral is. Negative g r squared. The integral of a quantity to the power of -2 is the quantity to the power of -2 plus 1 divided by -1. Well, that has the effect of turning that into a positive. So in fact, let's get rid of that unnecessary information. And now we have an expression for velocity in terms of its distance, the velocity of an object in terms of the distance of the object from the surface of the earth, right? R is the radius. This distance here is the distance from the center of the earth. So x is the distance from the surface of the earth. R is going to be a constant. Okay, I want to take one more step at this stage and just tidy this up a little bit. I want to write this with a positive exponent. And then I've left something off, not intentionally, but it's worth noting. I forgot a plus c, and that's going to be important. We're going to need to figure out what that is under certain conditions. We have some initial conditions. We'll be able to do that. But before we do, I want to remind us that this expression is in terms of x, the distance from the surface of the earth, and it's normal to think of velocity as having a variable of t, velocity of t, v of t. That's what we tend to do with velocity. In this case, though, we changed it up a little bit. Down here, we wrote dv dt as dv dx times dx dt, and we kind of got rid of dx dt. We called that velocity, the change in position over time. That's what velocity is, right? So we called that velocity, and then we went on to multiply. But this expression here, this dv dt, v dv dt, implies that v is now written in terms of x. And we did that so we'd have the same variable on both sides of our equation, and that means that this is velocity in terms of distance from the surface of the earth, not in terms of time. So we need to figure out, if we know what our initial velocity is, we need to do it in terms of distance. We were given that initial velocity, which means v of 0 equals v naught, or v sub 0. And this, again, is implied to be t, just because that's how we think of velocity. That's what our initial velocity expression was. And so in the original statement of the problem, this initial velocity is in terms of time. However, fortunately for us, as we're firing off our projectile, we can notice that at time t, the distance away from the surface of the earth is also 0. When time is 0, x is also 0. So I'm going to write this off to the side. T equals 0 implies x equals 0. And that means that in this case, this statement is true regardless of whether this is t equals 0 or x equals 0. That's very fortunate for us because it just makes our next calculation easier. If instead of firing this from the surface of the earth, you were firing it from say, a window 100 feet above a building, above the ground, and you started your projectile there, or actually I guess it needs to go straight up, then v of t would be initial velocity when time was 0, but not when distance was 0. Because when distance was 0, that would be way back here, right? So it's important that we consider this specifically because we changed the variable, we changed the independent variable we were working with on the left-hand side so that it would match. And that means we need to consider this on the other end of the problem when we try to figure out what our initial velocity is. So we have, get rid of some of this, we have that v squared over 2 equals g times r squared over x plus r plus c when x is 0. Let's put that in a different color, why not? When x is 0, the initial velocity is v naught, or v sub 0. So I've changed those two values in my formula, noting that this makes the denominator super easy here. It still looks like a variable. It looks like I still have a c and a v in here, but this is a constant now. V naught is a constant. So I can solve this for c by, this is just going to be r in the denominator. I have v naught squared over 2 equals g r squared over r plus c. This simplifies a little bit. V naught squared over 2 equals minus gr. Going a little too fast. That's what happens when you go too fast. Minus gr equals c. And so now I have a value for c. It's v naught squared over 2 minus gr. That means I can plug that in here. So let's do that. V naught squared over 2 equals g r squared over x plus r plus c, but c I now know is v naught squared over 2 minus gr. I've just noticed another mistake. I get to be human. It's Thursday. Thursdays are my day to be human. When I plug my c value, that c value that I found back here, I'm plugging it into this equation. And in this equation, this is not v naught, but v. Just like this is not 0, it's x. This is not v naught, it's not a value, it's v. So I need to erase the subscript on my, wrong pen, sorry. I need to erase the subscript on my v there because it's incorrect. All right, now I'm going to simplify things a little bit by multiplying both sides by 2. I get v squared equals 2g r squared all over x plus r plus v naught minus 2gr. I've just multiplied both sides of the equation and distributed a 2. I'm going to get rid of some of this and add a little bit to my dividing line here. Taking the square root of both sides, I get v equals, now this is v of x, let me write it that way. V of x equals plus or minus the square root of, see, can I squeeze this all in here? I just found another mistake. When I doubled this, I got that. When I doubled this, I got that. I forgot to square my v naught. I put a v superscript 0 instead. Going too fast. Slow down. Need to slow down. Okay. My pen's not working. V naught squared. There we go. So I have v naught squared plus 2g r squared over x plus r minus 2g r. Boy, I hope you can see that. I just barely made it in terms of the space I needed to do the job there. Okay, this is my answer to this part of this question. As the question is stated here, this is the answer. There's more to it in the textbook, but we'll come back to that in a minute. This is the velocity of an object projected straight up from the surface of the Earth when it has reached a distance of x units. I don't know if we're in miles or feet here, it doesn't say. X units from the surface of the Earth. This is how its velocity is determined. Its initial velocity, whatever that happens to be, plus an expression involving a constant for acceleration due to gravity, a constant involving the radius of the sphere. In this case, it's the Earth. I guess that's it. The G and the R are both this. So this is the only variable here. This is a constant. G is a constant. R is a constant. X is the only variable. So this is our velocity. The expression for the velocity we were asked to find. That is our answer to that part. It's worth noting we have a plus or a minus here. If I don't know how many of you have taken calculus or physics or at what time or how long ago. So just as a quick reminder, velocity is measured as being positive if you are moving forward, essentially. So if you are facing forward and you take steps in that forward direction, your velocity is positive. If you are facing forward but walk backwards, then your velocity is negative. So in this context, we would say that we want to use the positive sign for the velocity of any object being fired from the surface of the Earth. If it's being fired away from the Earth, we're going to use the positive. If we're going to use a dynamite to fire it into the Earth, we would use the negative. So that's how we would use that information. The other two parts of this question are to find the initial velocity required to lift this mass, this bowling ball or whatever, to its maximum altitude. So in other words, find the maximum altitude above the surface of the Earth to which this thing can attain, right? So what is the maximum height? What is that maximum height? How high can it go? And then what is the velocity specifically that would be required to get it there? Now, we don't have a number because we don't have a mass. The different masses will reach, with the same initial velocity, will reach different altitudes. So we just call it A max, altitude max, or A sub m you might want to use. And with that sort of generic constant value in place, we find another expression that says what that initial velocity has to be to get it to that height. And then lastly, we're asked to find the least initial velocity for which the body will not return to Earth. In other words, the escape velocity. So I know I started this video by defining escape velocity, but that's really the last part of the question. And I almost feel like the last two parts of the question are really quite nicely handled in your textbook and are not difficult to follow. Simply take, for the first one, finding the velocity required to get this thing to its maximum height, change x to a, or a sub m, for altitude or maximum altitude. Leave v sub naught, because that's an initial velocity, that's constant. Acceleration due to gravity and radius are both constant. Leave those alone. Just change this to a, or a sub m, and change velocity to 0. Because when it reaches its highest point, it's going to start coming back down again. In other words, velocity, which is a change in position, outward and inward position over time, that change in position is just for an instant going to be 0, right? Imagine a parabola. When you get to the top of the parabola, you have a 0 slope. That's what's going on there. The thing reaches its highest altitude, stops climbing, stops changing direction in the positive direction, and starts falling, starts changing direction in the negative direction. So its velocity becomes 0 at some maximum altitude. Make those two replacements, solve for v naught. That's all you have to do for that part. And then for the last part, you take the v naught equation that you have found by making those replacements and solving for v naught. You'll have an equation that says v naught for this particular situation, v naught equals, and you should get 2gr times a, they say a max, I'm going to call it am, r plus am, you get that equation. And what we're looking for here is what is the maximum velocity in this, or sorry, what is the maximum distance in this case? Well, we want to, the thing is going to be very, very far away. In fact, theoretically, there's no time, there's no distance away at which the gravity of the Earth has no impact on this object. There will be other objects in space. There will be there's the mass of the thing itself. If there's a point at which its own mass is sufficient to overcome gravity. There's a lot of things to consider here. But if you take this expression and assume that a sub m or a sub max goes to infinity, right? That this thing is infinitely far away, then this number, infinity, is so much bigger than r that the plus r piece here becomes inconsequential, right? It becomes negligible. And so we can say that this is, to all intents and purposes, so close to 1 as to be indistinguishable. And so we say that the escape velocity is equal to the square root of 2g r, where g is the constant representing the acceleration due to gravity, and radius, r is the radius of, in this case, the planet Earth, depending on what planet you're on or what sphere you're firing from or what the other forces are. That might be different, but whatever it is, it's a constant, and g is a constant, and 2 is a constant. You take its square root, it's a constant. Escape velocity, I think this is really quite interesting. Escape velocity is a constant. And on Earth, that number turns out to be approximately 11 kilometers per second. So 11.1 kilometers per second. That would have to be km per second, which is equivalent to approximately 6.9 miles per second. I think that's really quite fascinating. It doesn't matter how heavy the thing is. To fire something, anything, a pea, a bowling ball, a rocket, out of the Earth's atmosphere, you have to fire it at 11.1 kilometers per second. Isn't that interesting? So I said I wasn't going to talk about this piece, and I guess I kind of did that anyway. Made the video even longer than I think is, strictly speaking, necessary, but still we managed to finish the example, and with that we have finished the section. So I will see you in the next section.